particular, I want to summarize the location of the poles, and from there to tell the response of the systems. Okay, so basically, I'm going to correlate the system response to the location of the poles, and that one will help us to visualize the system response by simply looking at the location of the poles. We start with a system. This is called the first order system. And in the plot transform or in transfer function, we have this. And if we would take the plot transform of this one, then that will get is this. And this is called the first order system. And why it's called the first order system? Because the transfer functions given this is a s plus a. Okay, so this is a transfer function. For example, this is the output, and let me call the output is y. And to input, which is r. Okay, and let me show you why this is a first order system. So simply I multiply in this, so s plus a times y over s, and equal to a times rs. Okay, and so s times y plus a y equal to a times r. Here I drop off the function of s here. So then I take the inverse of plot transform. Then s multiplied with y. If you remember, if we have the derivative, then the plot transform is s and minus y0. Okay, so here for initial conditions, we drop the initial conditions in transfer functions. So basically here is, and in the time domain is y dot, and plus a and y in the plot transform is y. Okay, so that is a, and the plot transform of r equal to this. So from here you can see this is the first order system. Okay, so basically if transfer functions have this type, then basically we have the first order systems here. And by drawing the response of this function only, we can see that is the exponential decay, no oscillations. Okay, and also the decaying rate basically is governed by A. The larger the A, it decaying faster. The smaller A decaying slower. Keeping in mind the value of the A, so from here you can see if this pole, for this case the pole located at minus A here. So if this location, the location of this pole is farther on the left hand side, then this response will be quicker. Okay, so that means for this case, we can see is in the S domain, and here let me call this is the minus 1, and compared to the other system, say that is at minus 10 here. So for this case, we can see the response in the time domain, and let me call the system A, and this one let me call the system B. So for system A, its response will be something like this. And for system B, that response will be something like this. So from here you can tell by telling the locations of the pole, we can pretty much have the intuitive feelings about the response of the system. Okay, so keep the kind of the trend in mind, and then we're looking at the second. So this is the second order system. The second order system, basically, the transfer function in general have this type. And again, before we look into why it's a second order system, we first we do the Laplace transform of this one. We will get is this, okay? And if you do the symbolic, basically here A1, B1, here is certain numbers, okay? So here this is a general form. And of course, the number here, A and B and C, they really not match with something, but we can always find it, the relation. So this is a template. I would say this is a template of the response in this way, in sinusoidal functions, and which is oscillating. And oscillating in a frequency B, And also that oscillation is decaying, that is enveloped by this. So let me show the general response. Let me try to draw it here. So that one basically is so for response, something like the x of t equal to a, that is the magnitude at and sine bt plus v. Okay. So in general, the response can be like this. So this is the time domain, and this is the x of t. So basically, this is the magnitude of the oscillations. And the oscillation is in sinusoidal functions. The oscillation basically is governed by, this is the frequencies. Okay, B is this one. Okay, so this is the magnitude, and magnitudes basically have the features that is something like this, and in exponential decay, starting from the magnitude is A, because when t equal to 0, the magnitude equal to A. So this is the envelope E minus 80. Good. And then oscillating, basically here is this oscillation. So that means starting from here, because here when t equal to 0, sine phi has a certain numbers, could be positive, could be negative, but anyhow, let me draw it. So that is the oscillations of the sinusoidal functions, and gradually the magnitude decaying. So from peak to peak, this is the period. Okay, period basically period of oscillations. And by definition is 2 pi divided by the frequencies B. Okay, so that means the larger the magnitude of B, then the period will be smaller, which means oscillating very quicker. Okay. So that is the information like this. So one example could be like this. For this drawing, basically the phase angle phi equal to 0. Okay, so that is the drawing, the features in the time domain. And now we want to convert the information in the frequency domain. So that means we plot the poles on the complex plane. That is a real S. This is the imaginary S. So the poles are is S equal to minus A minus plus in B. Okay, like this. Okay, so this is the real part. B is the imaginary part here. Okay, just like we're showing. So from here, can you tell the magnitude of the real part here? So this is the real S, and this is the imaginary S. So here, this is minus A, and that is the real part here. So that is the real part here. Okay, and that is B, and this is the imaginary part. And so here, that is location. Let me highlight using this. Okay, that's a complex conjugate. So basically, that's symmetric with respect to the real axis. So from here, you can see by simply looking at the locations of the poles in the complex plane, we can pretty much get a feeling. Basically, the size of the real part, which is negative, tell us how quickly the decaying would be. The size, the magnitude, the value of this one tell us how quick the oscillation would be. So here we can make one example here. So say if we have a system, so say this is for the system A. Okay, compared to the system B here, so let me say the system B is here. Okay, the other one is here. So let me simply look at here. So this corresponding in the system B have the second order poles here. So for system B, can anyone tell? For system B is decaying is let me do that one. So system B have the slower decaying profile. Can you see? Because system B has a smaller real value. So for example, here system A is minus 10. If this is minus 1, but that means the E minus 1 compared to minus 10. This is system B, this is system A. So for system B, it has much slower decay. Can you see? Okay, so that is the system B here I drawing. For system B, you can see system B has the more larger the B value than system A. So for example, for system B, for system A, let me make one example. This is sine, say 1t. For system B, it has a much larger B value. So let me say sine, say 20. So for system B, because it has the larger imaginary part, so oscillating will be quicker. So that means, let me make up one. So system B could be something like this. Something like this. Sorry, I should be going down further, but anyhow. Be good? Okay, so here, this one, basically by simply compare the location of the poles from one system to another, you must have to quickly build up the sentimental pictures about what the system would be. Okay, and that will help you to further analyze the remaining things. Any questions about this? And pretty much why this is a second order system, and you might give yourself a try. So for example, for a given transfer function, let me make up one. So say if this is 1, and s squared plus 2s plus 3, okay? So this is one special case of this. Okay, I simply make up one example there. So for example, this is a transfer function that is the output respect to the input. In the same thing, you can prove it s squared plus 2s3 and ys will be equal to rs. So here, taking the plus inverse, that means y double dot plus 2y dot plus 3y will be equal to r. So from here, this is very clearly that is a second order system. Okay. Then, yeah, you can keep looking, and we can keep looking this one. So for this case, you can see this is a transfer function, the difference of this denominator with the previous one, and looking at your handouts, because for this one, it has no s term. Okay, that is a difference compared to the previous one. So for this case, the poles simply is the pure imaginary part. That means the s equal to plus minus j times b. So that is here. So this is a special case of the previous example here. There's no real part. No real part, that means the system response has no decay because a equal to 0. Okay, so clearly the system will be like this. And here the oscillation frequencies basically is exactly equal to b, and b is in the unit of the radian per second. Okay? For this one, this is, again, this is the first order system. And first order system, we can see what kind of the first order system. So say this is the transfer functions, and a s minus a, and that is y over r. So therefore s minus a y equal to a times r, and then we take the plus inverse, so that means y dot minus ay equal to a times r over t. Okay, so that's a function of t. So this is the first order systems. And compared to the two pages, 2 slides before, And that is the one we see. That is y dot plus ay equal to a times r over t. So that is the one we seen a couple of minutes ago. So the difference is this sign. Okay, so for this sign, you can see if we take the Laplace transform of this one corresponding is this. So the difference between the previous, from the previous example is you can see the response is growing up until whatever the basically the magnitude is going to float up, which means approaching to infinity. So for this kind of case, we call the system is called the unstable system. Unstable system, that means the system's response or outputs keep growing, become larger and larger. For anything for the control, we wish the output to be stabilized to a certain value. Okay, so here in terms of the design, we call this called system unstable. Unstable corresponding to that has the, you can see the location of the pole is s equal to a. Sorry, here is a typo here. So that means, for example, if a equal to positive, then we have the real positive real part. For any system that has a positive real part, it always has an exponentially growing response. That is undesired. For this kind of response, it is always undesired in control systems. Okay. So for this slide lesson, as long as there are any poles on the right-hand side of the complex plane, the system will become unstable. We mean unstable, that means the magnitude will growing to infinity. Okay. So not only matter is on the real axis, but we can see the next page for another case of unstable system. That is a second order system. And again, for this second order system, we still have the positive real poles. The poles have on the right hand side. So as long as on the right hand side really doesn't matter, that it still have a trend in growing to infinity. Okay. So this system is unstable. You okay? Good. So this page basically is a very good one, and I think this page, if you can mentally see this page basically summarizes everything we have done so far, and this is a good one. Okay, so that quickly tell you the kind of schematically how the system will look like. So the lessons from those kind of analysis is once you see any transfer functions, any type of the transfer functions, hopefully you can quickly build up to tell in your mind right away whether the system is unstable or not, and then what the system response would look like. And refer to this slide. Okay. And again, most of our systems to be discussed in ME409 are second order systems, up to second order systems. So basically this page, this slide will be good enough for most of the studies. That's it, and the remaining will be the state space modeling, and this part I won't be